So if you look at number 8, this is saying, is it a function, yes or no, and then determining the domain and the range. So remember, functions are things that pass the vertical line test. You only want each input to have one output. And no matter where I move a vertical line on this graph, it's only going to touch that quadratic one time. Therefore, it is a function. It passes the vertical line test. The domain are your input values. These are what you are using for x, how far left you're going, how far right. And I always phrase it, is there a wall stopping you on either side? And while I can draw those, and there's nothing stopping me from drawing them, remember these arrows mean it keeps continuing in this general format, which means it doesn't keep going vertical, or it doesn't hit vertical, that is. It keeps expanding outward. So even though I thought I could draw a wall here, it breaks through those walls. Every quadratic graph will have all real numbers as its domain. It will use every single x value, the negatives, the zeros, the positives, all numbers are part of the domain here. That is not true for the range. So the range is asking, is there a floor, is there a ceiling, or does it just keep going forever upward, forever downward? And it doesn't, because remember, this is a graph that starts out decreasing, hits a minimum, and then flips to increasing. Because of that change of this minimum, we have a floor. We have a y value that you will never cross below. So that y value is a y value of -2. So my range is any number that can be above that. So I'm going to put a greater than. But also, there's no open circle here. So we are left to assume there is a point here that is at that minimum of 2, -2. So don't forget to use equality when we talk about the ranges here. Those y values can be greater than -2 or equal to -2, but never below. For E, this thing is a function. Every input will only have one output. It will pass the vertical line test. When I talk about domain, I'm talking about, is there a wall that I never cross on the left or the right? And there's not. Those arrows are clearly communicating to continue in this fashion. So because of that, my domain is all real numbers. There's no limit to what x values are in use. There is a limit to your range. So this is the question about floor or ceiling. The one that I don't think is up for any debate is the floor. It is clearly sitting on the x-axis. I start out decreasing, I pause at this minimum value, and then I flip to increasing. When you flip directions, a lot of times you are going to be limiting your range. So I'm seeing that my y values, at their very smallest, are sitting on the floor of 0. Now, the upper value I could see up for debate of whether or not this just goes horizontally or if it's this bouncing pattern forever. Like, it's kind of hard to tell for sure what it is doing, but because it just says an arrow off in this direction, I'm left to assume it's going to keep doing this. And you'll notice my initial thought of maybe having a ceiling here at -3 is now out the window. Because if you assume that it just keeps gradually going upward and outward, you are going to cross that potential ceiling. So I don't want to put any limit at the top. I just want to basically say, so there's no limit here, but there is a limit here. So the way that actually makes more sense to write it, I was trying to think compound inequalities, but it would make much more sense to just write that y is greater than or equal to 0. So I probably should have waited to write it down until I'd already thought through it, but it's too late now. So on part F, this is not a function. When you draw a vertical line through this graph, there will be multiple outputs for one input. At this input of 1 for an x value, my y is sometimes -1, my y is sometimes +1. You can't have 2 inputs for one output and call it a function. So when I talk domain and range, the domain will not be all real numbers. There's no arrows anywhere. So there's going to be a wall on the left and a wall on the right. So we can see here it never goes smaller than this. And by this I mean -2. I never go beyond this number. And on the right, I never go beyond +2. So I'm coming up with a range of values, a list of values for my x's. And as I said in class, I ignored this temporarily and just write my symbol. And I can see that x has to be less than or equal to 2. The reason I included equality is because over here, there is no open circle or anything communicating that it's not actually sitting here. There is a point on this graph, on this relation of 2, 0. So I'm going to say, yeah, it can equal 2. When I go to the other side, the other wall of -2, on that graph, there are 2 open circles, which means it never actually equals -2. So it gets really close to it, but if you don't include it, that's when you use the open circles. So my domain is anything between -2 and 2, where you can equal 2, but not -2, and anything in between. When I talk range, this is floor and ceiling. We can see these pretty easily because there's no arrows on this one. And I see, again, just like the y's, it's a 2 and a -2. That's just a coincidence. But I also see where that sideways U shape hits this ceiling, there's the open circle. Where this sideways U shape hits the floor, there's an open circle. So I will not put lines under my inequality signs. So it will look like this one, not, oops. It'll look like that one, not this one is what I was trying to say. So if I'm trying to figure out which directions these face, first of all, they always face the same direction. But when I'm talking about my ceiling, then I can see that it is less than that 2, not equal to. When I talk about, let me erase some of my lines everywhere. When I talk about my floor, so the floor is here, it is greater than, which seems like I wrote it backwards, but remember I'm saying y is either this or y is that. So when I read it, I'm saying y is greater than -2. Hopefully that one made sense. And then the last one is similar, hopefully, to some of the Mathia things that you had worked through, where there's inputs and outputs. This is actually in context of the distance that's being traveled over time. So I'm putting in a certain time, and it's changing how much I've traveled. So the first one we said, if your time is 1, your distance is 10. That's basically saying I see the point on this graph of 1, 10. This is what it means in context. So the next one, the input is a 2. Well, when 2 is put in, out of this function, a 30 comes out, which means h of 2 is 30. After 2 hours, the distance traveled is 30 miles. Similarly, I'm going to look for what my output is when my input is a 5, and I can see that here on the graph. When x is 5 or h is 5, then my output is a 70. After 5 hours, the distance traveled was 70 miles. The last two flip this around, they're already giving me the mileage. So they're saying, okay, the output was 50. When was the output 50? So if I look at 50, I can tell that was at 4 hours. So they're giving me the output. We can figure out that corresponds with a 4-hour travel time. And that's really similar to the last one too. They're telling me the output was 40. I can look on the graph and see that happened at the 3-hour mark. So after 3 hours, after 3 hours, the distance traveled was 40. So h of 3 is 40.